Okay, so I'm a PhD student at the Australian National University, and today I'm just going to give an overview of a study that we're working on, which is looking at the longitudinal effects of physical activity change on brain volumes. So in terms of exercise is thought to be good for the brain, and there's been quite a lot of studies, intervention studies, that have shown a positive association between increasing exercise and higher brain volumes. But with the interventions, they've all been reasonably short term, with most interventions being 6 weeks or 6 months, and only a few lasting as long as 24 months. So while we know in the short term increasing exercise has positive effects on brain volumes, the long term effects are not quite as clear. So with the study that we've looked at, we've used a population cohort that's based in Canberra that was being followed for up to 12 years, and we followed 411 middle-aged participants who were 44 to 49 years of age at baseline, and 376 older age participants who were 60 to 64 at baseline. And we followed them for up to 4 years with MRI scans and tests every 4 years. In terms of physical activity, at each time point, we asked them how many hours of light, moderate or vigorous activity they had performed in the previous week. And we used that to calculate the amount of global physical activity they were doing, and to calculate the difference, the change in physical activity between the time points. For the brain volumes, we looked at the volume of the hippocampus, and the hippocampus is an important brain structure that's involved in memory formation, and it's affected also by many illnesses and lifestyle factors. So depression, schizophrenia, Alzheimer's disease, Parkinson's disease are also associated with reduced hippocampal volumes, and also hippocampal volumes change during life, and particularly from about age 50 onwards, the volume of the hippocampus shrinks by up to about 1% per year. Now, the hippocampus is a bilateral brain structure, which means there's two of them. There's one on the left and one on the right. There's the base of the brain towards the centre, and it's around about where the ears are. So we looked at what the associations were between the physical activity and hippocampal volumes between each time point. And what we found was that over the period of the follow-up, there was a positive association between increasing exercise and hippocampal volume, and the effects were very small, were quite small, but in the middle age, in the right hippocampus, the effects were significant, which is the orange bar shown there. And next we looked at what happens over time, and what we found was that the volumes changed, the effect reduced over time. So on the graph on the right, the dotted line is hippocampal volumes where there's no change to exercise over the period. And the solid line is an amount of exercise equivalent to an extra hour of moderate physical activity. And what we can see here is that over time, that the two lines get closer together, which means that the gap between doing nothing and having increased the exercise is reduced over time. We also looked at what the effect was for people who are at risk of Alzheimer's disease. There's a particular genetic risk factor called ApoE4, which about between 10 and 25% of the population have, and it's one of the larger risk factors for Alzheimer's disease. And when we looked at the people who had this genetic risk factor, we found that that the effects of exercise were greater for those people. So just to summarise, so what we found was we found over the follow-up of the 12 years that there was a positive effect of exercise, but the benefits declined over time by about 10% a year. And the implications for this is that if we were wanting to design exercise interventions that enabled, that helped people age, maintain brain health as they age, we need to focus on programs that will create long-term exercise habits. And finally, that increasing physical activity may be especially beneficial for people who are at risk of Alzheimer's disease. So I'd like to acknowledge my co-authors and supervisory panel and the people who have contributed to our study. Thank you.
Thank you, Mark, for your presentation. I have one question, and the question is, were other brain regions related to coordination, like, for example, the cerebellum, or physical activity considered in the analysis, and why focus only on the hippocampus? And the comment is also that was a great presentation.
Yeah, the hippocampus is one of the sort of most studied brain regions because it's sort of sensitive to many changes, and it's also big enough to be able to measure changes on MRI scans. It's also one of the first areas where Alzheimer's disease, the pathology associated with Alzheimer's disease and dementia starts. So that's been one of the key reasons. With this particular study, we mainly traced the volumes of the hippocampus. So the study started before a lot of the automated volumetric measurement techniques had been developed. So we used manual tracing for all of the scans, 2,000 odd scans over the period, and it's supposedly it's thought to be the gold standard for measuring brain volumes.
All right, thank you. Great answer. We don't have other questions, so I'll thank you for your presentation.